Hi, welcome to Sunil Maths tutorial, functional analysis class number 41. In this video, we learn some definitions and one theorem. Let us see. The first definition, unit vector. Unit vector. Everybody knows this definition, but in terms of Hilbert space, we learn this. Let capital H be a Hilbert space, H be a Hilbert space, and take an element small x belongs to capital H such that norm x is equals to 1. It means inner product of x comma x is equals to 1. In such a case, the vector x is called unit vector. The vector x is called unit vector in capital H. It is also known as normal vector. It is also called normal vector in capital H. Let us see again. Capital H is a Hilbert space. An element x belongs to capital H. X belongs to capital H such that it has a property norm x is equals to 1. Norm x is equals to 1 means inner product of x comma x is equals to 1. Then this element x is called unit vector or normal vector in the Hilbert space capital H. Next definition and very important definition, orthonormal set. Orthonormal set. Very important definition. Keep learning. So, a non-empty subset. A non-empty subset EI, small ei, of a Hilbert space capital H is said to be, of a Hilbert space capital H is said to be orthonormal set. Orthonormal set if it satisfies two conditions. If it satisfies two conditions. The first condition, norm ei is equals to 1 for every i. For every I, norm ei is equals to 1. Norm ei is equals to 1 means, the vector ei is a unit vector. The vector ei is a unit vector. That's the point. And the second one is, for I not equals to j implies as every ei perpendicular to ej. Every ei perpendicular to ej for I not equals to j. For I not equals to j, every ei is perpendicular to ej. It means inner product of distinct vectors is 0. Inner product of ei comma ej is equals to 0 for all I not equals to j. It means every pair of vectors are orthogonal to each other. Every pair of vectors are perpendicular to each other. It means ei perpendicular to ej for all I not equals to j. That's it. Orthonormal set. So, a non-empty subset ei of the Hilbert space capital H is said to be orthonormal set if it satisfies two conditions. The first condition, every vector is a unit vector. It means norm ui is equals to 1. And every distinct vectors must be orthogonal to each other. It means inner product of ei comma ej is equals to 0 for I not equals to j. That is, ei is always perpendicular to ej for I not equals to j. That's it. So here you remember some important points. Let us see one by one. The first one, if H contains only 0 vector, if the Hilbert space H contains, H only 0 vector, if the H contains only 0 vector, then it has no orthonormal sets. So it means H has no orthonormal subsets. It means you observe that orthonormal set does not contain a 0 vector. Orthonormal set does not contain a 0 vector. That is the point. So remember the second point. There is another point to remember. Second one. If H contains a non-zero vector x, then then x by norm x by norm x is clearly this set, this singleton set must be an orthonormal set. If x is a non-zero vector, it means x is not equals to 0. Then the set having only one element x by norm x by norm x must be a orthonormal set. This set must be an orthonormal set. An orthonormal set, remember that. So you can normalize the elements. If the vector is non-zero vector, then you can normalize it. Ei is equals to xi by norm xi. Obviously, you can observe that inner product of ei comma ei is equals to 1. Inner product of ei comma ei is equals to 1. And it is perpendicular to another elements also. So let us see one very good example for this orthogonal set. And the first one, example number 1, the subset e1 comma e2 comma and so on en of L2 power n comma where ei is the nth tuple with one in the ith place, and zeros everywhere, So you have to understand that E1 means 1 comma 0 comma 0 and so on 0. E2 means 0 comma 1 comma 0 and so on 0. E3 means 0 comma 0 comma 1 comma 0 comma and so on 0 and so on. So EIs are elements like this. EIs are n tuples with 1 in the ith place and zeros everywhere. So then this set, you observe that inner product of ei comma ei is equals to inner product of 0 comma 0 comma and so on 1 comma 0 and so on into 0 comma 0 comma and so on 1 comma 0 comma and so on is always equivalent to 1. It means ei is a unit vector. And also ei is perpendicular to ej for all I not equals to j, because inner product of ei comma ej is equals to 0. So from these conditions, two unit vector and they are perpendicular to each other, this set e1 comma e2 comma and so on en of L2 power n is an orthonormal set. To understand more precisely this set, you observe that 1 comma 0 and 0 comma 1 is an orthonormal set. 1 comma 0 comma 0, 0 comma 1 comma 0, 0 comma 0 comma 1 clearly is an orthonormal set. So I think you understand this pattern. 1 comma 0, 0 comma 1, 1 0 0, 0 1 0, 0 0 1. This is also an orthonormal set. So we go for one more example. Example number 2. So let us see example number 2. After that we learn a theorem also. In the second example, En is a sequence. If En is a sequence within the nth place, and zeros everywhere, En is the sequence with 1 in nth place, and with n in nth place and zeros everywhere, then this set is an orthonormal set in L2 power infinity. So remember that L2 is an infinite set having elements e1 comma e2 comma and so on, en comma and so on. Clearly this collection is an orthonormal set in L2 space. or L to power infinity simply. So now we are going to learn a theorem and see the statement of that theorem. Let us see the statement. Let E1 comma E2 comma and so on En be a finite orthonormal set in a Hilbert space capital H if x is any vector, in capital H, then summation over I is equals to 1 to n mod inner product of x comma ei whole square is less than or equals to norm x square. Further x minus summation over I is equals to 1 to n x inner product of x comma ei into ei is perpendicular to ej for each j. We prove this theorem. Let us see the statement again. E1, E2 and so on En be a finite orthonormal set in the Hilbert space capital H and x is any vector in H, then summation over I is equals to 1 to n mod inner product of x comma ei whole square is less than or equals to norm x square. Further, x minus summation over I is equals to 1 to n inner product of x comma ei is perpendicular to ej for each j. So right, now we prove this theorem and it is a simple calculation. Let us see. They given that the set E1 comma E2 comma and so on En is an orthonormal set in capital H. By the definition of orthonormal set, inner product of ei comma ej is equals to, you have two values, 1 if I is equals to j, 0 if I not equals to j. That's it. Inner product of ei comma ej is equals to, by the definition of orthonormal set, inner product of ei comma ej is equals to 1 if I is equals to j, 0 if I not equals to j. Excuse me. Now consider an element small x. X belongs to capital H. Take an element in the Hilbert space x belongs to capital H and 0 less than or equals to norm x minus summation over I is equals to 1 to n inner product of x comma ei into ei whole square. This is everywhere true because of norm is a non-negative function and its square is also non-negative function. So which is clearly equivalent to square means inner product of x minus summation over I is equals to 1 to n x comma ei into ei comma x minus summation over I is equals to 1 to n x comma ei into ei. This is from definition of inner product. Norm x square means inner product of x comma x. Norm x square means inner product of x comma x. Here also we have norm x minus summation over I is equals to 1 to n x comma ei into ei whole square. So I can write like this, inner product of the same element. Now split the inner product. By splitting the inner product, you get this inner product of x comma x minus summation over I is equals to 1 to n inner product of xi comma inner product of x comma ei comma ei, ei comma ei minus 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 summation over I is equals to 1 to n inner product of x comma ai into inner product of ei comma into inner product of ei comma same element, complete element, x minus summation over I is equals to 1 to n inner product of x comma ei comma ei. That's it. Again simplify. This is nothing but inner product of x comma x minus summation over I is equals to 1 to n inner product of x comma ei bar into inner product of x comma ei minus minus summation over I is equals to 1 to n inner product of x comma ei into inner product of ei comma x minus into minus plus summation over I is equals to 1 to n inner product of x comma ei into summation over I is equals to 1 to n inner product of x comma ei bar into inner product of ei comma ei. So again this can be written as which is equals to norm which is equals to inner product of x comma x minus summation over I is equals to 1 to n inner product of x comma ei bar into inner product of x comma ei minus summation over I is equals to 1 to n inner product of x comma ei into x comma ei bar plus summation over I is equals to 1 to n inner product of x comma ei into inner product of x comma ei bar. You observe that these two terms are same with the opposite signs. Here it is minus, here it is plus. Same terms with opposite signs, so they get cancelled. We get the remaining terms only. We get two terms only. The two terms are inner product of x comma x minus summation over I is equals to 1 to n inner product of x comma ei bar into inner product of x comma ei. So again this can be written as norm x square minus summation over I is equals to 1 to n mod inner product of x comma ei whole square. So in the left side you have less than or equals to 0. In the left side you have less than or equals to 0. What it means? Norm x square minus summation over I is equals to 1 to n mod x comma ei inner product of mod x comma ei whole square is greater than or equals to 0. If it is greater than or equals to 0, what you get? Norm x square greater than or equals to summation over I is equals to 1 to n mod inner product of x comma ei whole square. So that is, you can rewrite the same term as summation over I is equals to 1 to n mod inner product of x comma ei whole square is less than or equals to norm x square. This completes the proof of our theorem. So, but in the statement we have, there is another one for the, you have to show that this condition. So, it is perpendicular to each, that element is perpendicular to each. So, to show that the element is perpendicular to each, you have to show that the inner product is 0. So, now calculate. Inner product of x minus summation over I is equals to 1 to n x comma ei into ei comma ej is equals to inner product of x comma ej minus summation over I is equals to 1 to n inner product of x comma ei into inner product of ei comma ei. We know that inner product of ei comma ei is 1. Inner product of ei comma ei is 1 and inner product of ei comma ej is equals to 0. So you get at I equal to I you get 1 and the remaining places you get 0. So this term simply becomes x comma ej minus inner product of x comma ej and the remaining terms must becomes 0 because of we know that these terms inner product of ei comma ej is equals to 0 because the set is orthonormal. So obviously this inner product is 0. What it means? If this inner product is 0, x minus summation over I is equals to 1 to n inner product of x comma ei into ei comma ej is equals to 0 means if the inner product of any two vectors is 0, then they are perpendicular to each other. So x minus summation over I is equals to 1 to n, inner product of x comma ei into ei is perpendicular to ej. This completes the proof of our theorem. In the next video, we will learn one more theorem. Keep learning. Wish you all the best.